All right. So far, we see that the magnetic field of a long straight wire that has current I at distance r from the wire, perpendicular distance r, is given by this, and you know the direction also. It is in azimuthal direction. Now, so this is a long straight wire, cross section of it I'm showing, and it has current I in it. I want to consider a circle in the plane perpendicular to this wire, which is the plane of the board. It's a circle centered at this wire. Let me put it right at the center. It's a circle centered at the wire and it's perpendicular to the face of the circle. Is perpendicular to the wire. So the wire is the axis of the circle, basically. And I want to calculate a line integral over this circle of b. So integral of d dot dl. If you take a dl here, you see now dl is not an element of current, it's just an element of length along this circle. I want to calculate b dot dl and integrate over this whole thing. Which direction is b of this wire at this point? Let's say this is r. B cross r is this, like this. B is this way. And dl is also the same direction. If dl is small, right? And then b dot dl becomes just b times dl, right? It becomes integral of b dl. And because b depends only on the radial distance, b is the same everywhere. So it becomes integral of mu naught I over 2 pi r times dl. And as this dl goes around to integrate, an integral is over a closed loop, just like circle, one turn around. This will be what? Mu naught I over 2 pi r, mu naught I over 2 pi r times integral of dl over the circle. What is the integral of dl? 2 pi r, right? So this is 2 pi r cancels out. So integral over this circle of b dot dl is equal to mu naught times I. Remember that this is the same as what we had for Gauss law. Gauss law says integral over a surface, closed surface of E dot dA is equal to total electric charge inside divided by epsilon naught. Now instead of 1 over epsilon naught we have mu naught. Instead of charge we have current, and instead of electric field we have magnetic field. But the integral is over a closed loop instead of being over a closed surface. But I want to argue that this is general. The current doesn't have to be in the center, it can be anywhere. And the loop doesn't have to be a circle, it can be any loop. Let's say there's a circle here, centered at this current, that's long wire this way, and there's another closed loop. And at any point, and a small angle that you take, the length of this increases by the distance, but b decreases by the inverse of the distance, so they cancel the effect of each other. And also, if this is at an angle, the length gets increased by cosine of theta, then for dot product you have to multiply by cosine theta, that also cancels out. So the E dot dl on this line is the same as E dot dl on this line. And then if you add all of these pieces together, you see the E dot dl around this closed path is the same as E dot dl around this circle. Therefore, this is general. And then if the current is outside, let's say there's a loop outside here. There's a loop here, but the current doesn't go through it. Again, if you draw a small angle like that, the E dot dl on this little part here is the same magnitude as this one, is the same magnitude as this one, right? But one of these is positive, one of them is negative. So these two contributions cancel each other. And then if you add all of these pieces, you see that there's net integral b dot dl along that path is 0. So for any current that's perpendicular to this plane, integral b dot dl mu naught I if the current passes through the loop is 0 if the current doesn't pass through the loop. So then you can make a general statement that total b dot dl for B created by all the current that are around is equal to mu naught times the current enclosed in the loop. And that's a general statement. Similar to Gauss' law, this is called Ampere's law. Again, we can use that when there is symmetry in the problem. We can go back now, if you don't know the magnetic field of a line, infinite line, you can use that and you can simply get that, because now suppose we don't know that, we just know this. For infinite line that is like that, you say that if there is a magnetic field, it has to be in azimuthal direction because of symmetry. And then you take a path with the radius r around it and apply this. B dot dl will be b times dl. So integral b dot dl, which is mu naught times I, becomes b times dl. So it becomes integral b dl, mu naught I. And then b is the same everywhere because there's symmetry. B comes out, integral dl becomes mu naught I. And then integral dl becomes L, which is 2 pi r. So b times 2 pi r is mu naught I. And then b becomes mu naught I over 2 pi r. Right, so this Ampere's law is equivalent of Biot-Savart's law that we postulated at the beginning, or the magnetic field created by a moving charge. But it is more useful because you can use it in some circumstances that's hard to use the Biot-Savart's law. For example, if you have a solenoid, solenoid is something like this. There are many, many turns of wire spread around the cylinder, not a coil. Coil is all on one circle, but this is many, many that go like this around the cylinder. And usually they are characterized by number of turns per unit length of the solenoid. And if this solenoid is long, means that the length of the solenoid is big compared to the radius of its circles or cylinder. You can use good approximation and find the magnetic field inside the solenoid. And usually it doesn't create any magnetic field outside because there's some magnetic field created by currents going one way and another created by currents going another way. They cancel each other out. So for a long solenoid, an ideal solenoid, if it has a lot of turns and it's long enough, outside magnetic field is 0. The magnetic field only has value inside. And we want to find that value. It is hard to do it using Biot-Savart's law, although it is possible to use Biot-Savart's law. But the Ampere's law gives us an analytical tool to calculate that. So let's see how we can use Ampere's law to calculate the magnetic field of a solenoid. So this is our law now. I just delete everything because you just need to know the law. And again, I emphasize this B is created by all the currents, not only the ones that are going through. And the integral depends on only the currents that are through it, and that is related to that. But the equation just tells us that. And so this is a general, like the Gauss law was general. All right, so let's say there is a solenoid like that, but it's long, infinitely long to be exact in our calculation. And outside magnetic field is 0, inside magnetic field is non-zero, and it has a certain number of turns per unit length of the solenoid. So usually we call that N. N is the number of turns per unit length. Like 10,000 turns per meter, or 1 million turns per meter. But if I want to cut this and show cross-section of it, I will see something like this. This is the upper part that is current in it, and there's lower part that is current in it. And let's say that the current's going like this, so out at any point here, the wires here, the current's coming out. The current is coming out on the top part, out of the page, like that. And the current's going in the lower part of this. So, right? Can you see? Imagine that. The solenoid is like this. The current is coming out this way, going in this way. And we're looking at the cross section of the circle. Alright. And you see each one of these loops create a current that is in this direction. So there's a, creates a magnetic field that is in that direction. And then we take an Amperian loop. The loop that we use to apply Ampere's law, we call it Amperian loop, like Gaussian circles, right? You take an Amperian loop like this, so that's symmetry, because we know that the magnetic field is along this direction. So magnetic field B dot dl only has contribution along this loop this way. And outside is 0, here is 0, here is 0, here is 0, here is 0. All these parts have 0 contribution to this integral. Only this part has contribution. And we call this length L, and B field inside, let's say B. And because of symmetry, so because it's infinitely long, the B field is along this all the same. So it becomes B times B dot dl becomes B times L. First becomes B dl because they are all in the same direction. mu naught I enclosed. And then B is the same everywhere. B comes out of the integral, becomes B times integral of dl becomes just the L equals to mu naught times I enclosed. Now, our task is to find what is the current enclosed in that loop. How much current is going through this loop? So we have to use this and the current in each loop to find the total current going through this Amperian loop. What do you think? This is number of turns. N is number of turns per unit length. So that means N is the number of turns per unit length. So what is the number of turns if you have length L? It's N times L, right? Simple. So, but for each turn we have a current I. So what is the total current? Total current enclosed is N times I. So that becomes N I times L. And then if you put that in here, B times L becomes mu naught N I times L. and L cancels out, B becomes mu naught n I. The magnetic field inside the solenoid is given by mu naught times n times I. If I is usually large, n is usually large, like in this, I don't know, maybe thousands of turns, but in 10 centimeters. If it is like it has 5,000 turns in this, as you can see, in 10 centimeters, then it will be 50,000 per meter, right? 50,000 turns per meter. So this n is usually a large number, like that, 50,000. Mu naught is a very small number. Mu naught is 4 pi times 10 to the negative 7, which is about 10 to negative 6, because 4 pi is about 10, 12, right? And I, current in amps. We have another thing called toroid. We don't have a toroid here, but look at this as a solenoid. This is a spring, but look at the wire as a solenoid going around. If you put the heads and tails of it together, it becomes a donut shape. Current is going like that, and they're going also around the loop. It's called a toroid. We said that the magnetic field is approximately 0, but it is 0 if the solenoid is infinitely long. For toroid, it is more closely 0. And if it is, these turns are closely packed, the magnetic field is 0 exactly outside. So it becomes more accurate. The magnetic field outside of this solenoid, if there's a current in it, is not 0 exactly outside because it's not infinite, right? But for a toroid, if it is closely packed, the magnetic field is 0 outside. It has only value inside. And if you want to calculate that, how much magnetic field is inside the toroid, it is like that, like a donut shaped. You look at the cross section this way. So you see some wires are going out of the plane, some wires are around and going into the plane. So if I want to look at the cross section, there's a inner circle, there's outer circle, the current here going inside. And it usually has n total turns in the toroid. The current in this, all of these wires are going out of the page. Let's say put dots on them so that the current is going out. And there are n of them. Then how do we apply Ampere's law? We can take a Amperian loop like this with radius r. And then argue that the magnetic field should be along the direction of this. So integral of along that b dot dl becomes just b times 2 pi r. That's equal to mu naught times I enclosed. And I encloses all of these. These ones are not enclosed in the loop. So these n currents going out of the loop from mu naught ni, and then b becomes mu naught ni, capital N, I, divided by 2 pi r. So that in the toroid, the magnetic field here decreases as you go away from the center by r. And it is, if the toroid is large, it's pretty much uniform, but it changes a little bit from here to here. And that's the value. This is magnetic field of a toroid. All right. So now, if you have a short solenoid like this, it has a magnetic field that goes like this. And it has north pole and south pole, and the magnetic field inside is in that direction. Can find it from right-hand rule. Inside is from south to pole, outside is the opposite, north to south. All right? The magnetic field is like this. And if you have a magnet also, it has the same kind of magnetic field. Inside it's up, outside is the other way around, so north and south. And these can be thought of as the same kind of magnetic field. As I said, it turns out the atoms, because there's an electron going around it, it has a magnetic moment, mu, and it looks like a loop of current, and it creates its own magnetic field again around it, right? That was fine. Say, okay, the electrons are going around, they create a current like what we have here. And then it turns out that the electrons themselves have a magnetic moment and have a magnetic field. So if you look at a very small electron, it has a magnetic moment mu. When they figured that out, they thought, okay, electron is like a ball of charge. It's rotating around, and it has a spin. It spins around, and each part of this is a little charge that's going around. It spins and creates magnetic moment, right? Makes sense. But it turns out that electron has zero radius. It is a point charge. It's not an extended lump of charge. So that picture is not valid, is not correct. Even with the dimensions that they knew like 100 years ago of electron, when they calculated that, they said that, okay, the surface of the electron has to go at faster than the speed of light to make the magnetic moment it has. So it doesn't really make sense. So when you go to quantum mechanics, this picture collapses. We cannot say the electron is a ball of charge that's spinning around itself. But the electron itself, it just has a magnetic moment. It's the same as we don't know where the charge comes from, what the charge is actually. We don't know what the mass is and where it comes from. Now they say it comes from the interaction with Higgs field. But that's an explanation that just is the same as why does it interact with Higgs field and why that. It's a mechanism that they thought of. And it's the same thing as we don't know, it's just another way of looking at it. So in the list of the things that we don't know about the elementary particles, we should add this thing that, okay, it has magnetic moment, we don't know where it comes from. Right? It has charge, it has mass, it has magnetic moment as well. It has all other things, you know, like lepton number, all these other quantum numbers that we talked about. So this picture that we talk about here, it doesn't make sense when you go to electronic or atomic size, but still you can think of a magnet having electrons going around it, so it creates a current, it has magnetic moment, and then when you have collection of atoms, inside the magnet, like this is a cross-section of a magnet, the electrons are going like this, all in one direction, let's say. And you see every volume that you take inside, there's electron going one direction, the electron nearby going the other direction. They cancel the effect of each other. But if you look at the surface, it's like it's all electrons going around it. Of course, at each point, the electron belongs to one atom. But if you go at any point, the electrons are moving around. It's like a current created. So to understand magnets, you can also think about as the electrons going around the surface of the magnet. So it's the same as the solenoid. So a magnet also, you can understand it as you understand the magnetic field created by a solenoid. So it's all the same picture, but we should be aware that this picture collapses when you go to quantum mechanics, like a lot of other things. So that's why we say we don't understand quantum mechanics. All right?